question is from the homework, and it's question number 5 in the homework, even though that didn't come through. And what they're asking is retrosynthesis, and retrosynthesis is working backwards. So if I were going to do a retrosynthesis of this thing, what you generally do is you draw a double-lined arrow backwards, and that arrow means that you're going backwards. So there are two things that I could go backwards to. One thing I could go backwards to would be putting the pi bond there and having the methyl group. And to do that, I'd want to get Markovnikov addition, or I could do addition to that alkene. So either one would work. And down here, the first option is the first alkene I drew, and they're adding HBr, and you're adding the bromine to the what would be the more stable, more substituted side, which is what you'd expect. The next one is a little bit more complicated, and I actually change molecules in the middle, but let me go through what the problem actually is, and then we'll go that you could get the same thing from putting the alcohol up there. So here, what's going to happen is in the first step, the HBr, which is a strong acid, is going to protonate the alcohol, making water, which is a good leaving group. So then you would get a carbocation there, and bromine would come in and attack. So that would get me the right product. That's 2. The next one is adding peroxide to the bromine, to the hydrogen bromide. And what that does is it changes the mechanism from being a carbocation mechanism to being a radical mechanism. And instead of going through the more stable carbocation, it goes through the more stable radical, and that gets you anti-Markovnikov addition, and it would not give you the product you want. It would give you the bromine out there. So that's not an option. In the next case, it's another example of Markovnikov addition, so this one would work fine. Then if I have HBr and peroxide, it would put the bromine over there. So that's not going to give me anything. And then this last one, you have to do something to the alcohol to make it a good leaving group. You either have to turn it into the tosylate or protonate it, but in this case, nothing is going to happen because that alcohol is just not a good leaving group. So that was the problem number 5. This is problem number 6. And so they want to form the primary alcohol. And to do that, this first example is not going to work because the water is just not a good enough nucleophile to do that. In the second case, where I do oxymercuration, demercuration, that is going to get me an alcohol, but the alcohol will be off of that carbon, so that's not going to work. Hydroboration will work, so that would be okay. This next one, concentrated sulfuric acid and heat, that gives you, if anything, an elimination reaction, but not appropriate here. And now in this case, I have hydroxide, which is a much better nucleophile. I've got a primary alkyl halide, and so that would work. So in this one, which is number 6, you have 2 correct answers. Limonene is found in many citrus fruits, including oranges and lemons. Draw the structures that you would get when you used a hydrogenation catalyst. So, and they don't specify whether you're using a soluble hydrogenation catalyst or not. And in fact, it doesn't really matter here because what you're going to do is you're going to hydrogenate the double bond here. So there'll be a methyl group. You're not impacting, let's see, there's going to be a methyl group there, and you're hydrogenating that bond. So you have 2 options. Firstly, you're not affecting the stereochemistry here because there's nothing that's getting hydrogenated, but you are affecting it up here, and it will come in from one side or the other side. So the methyl group from the top could either be coming out or going in. So you could form one where the 2 substituents off of the cyclohexane are on the same side, or where they are on opposite sides. So this would be cis, and this would be trans. And what you can see here is that the stereochemistry at this carbon and this carbon is the same in both structures, but the stereochemistry at the top would be different. So these will be diastereomers. So before I go on to the problems that I uploaded, I wanted to say a couple of things about what I did today. So I went back and I got some old WebExes where I was doing lectures online, and I've edited right now down and put up the second part of chapter 8. Within that, there is a discussion that I'm going to go through again here. I'm going to insert a couple of pages about the stereochemistry of adding bromine to a double bond. And I'm going to insert 2 pages. No, insert them. Maybe it did it after this page. It did, so we'll come back. So in lab, when we're actually face-to-face, we do the addition of bromine to trans-stilbene. And trans-stilbene looks like this. Coming out. So the way that I've drawn this is that the pi bonds are in the plane of the board, and the things with wedges are coming out towards you, and the things with dashes are going behind. So when you add bromine, so this would be adding bromine to a trans alkene. And by trans, I'm limiting it to the case where I've got the same groups coming off opposite sides of the double bond. So if you have different groups, this is a little bit different. So the question that we ask in lab is we're going to do the reaction, and I do it before we do this chapter. And then you use the results of this to determine whether you got syn addition or anti-addition. So I want to show you how that works, and it's important because you have to think of the stereochemistry here. So what happens is initially, I'll just draw the products. So we'll draw the products for anti-addition. And I'm going to abbreviate phenyl as pH, just because it's easier to do that. And now we've added anti. So there's a bromine here, and there's a bromine here. And let me think for a minute. This is R. And this is S. So I've done anti-addition to a transalkene, and because the substituents are the same on the here and here, there's a mirror plane in this, and this is a meso compound. And of course, I would get it the opposite way, where the bromine would come down on the first carbon and up on the second one. It would still be the meso compound. If we were to add syn, I would get mm-mm. So the configuration on the first one is still R. It's the same as it is above. And here, it's now also R. So if I do syn addition to a transalkene, where again, I've got the same substituents here and here, I'm going to get a pair of enantiomers. So I would also get the other enantiomer. So let's just put plus enantiomer. Now the two enantiomers have exactly the same chemical properties, but the relationship between the enantiomers and the meso compound is that they are distereomers. So when we do this reaction, we can tell which we got simply by melting point. Because they're distereomers, they have different melting points. They also would have other different properties, but the easiest one to access is melting point. So the thing to remember here is that if I have a transalkene, again, same substituents on both ends of the double bond, anti-addition gives meso. And syn addition would give enantiomers. So the fact that you only get the meso compound implies that this reaction is stereospecific. But to completely nail it, you would have to also do this reaction to the cis alkene. And I'll show you that they should also give you different products. So if we come down here and we consider, I'm just going to draw a line here, the case where we have cis, and now I'm going to do anti-addition. So on the first carbon here, I have R, and on the second one, I also have R. So anti-addition to the cis is going to give me a pair of enantiomers. And if you do it, so now we want to do syn addition. So this is going to be R, and now this is S. So syn addition to the cis is going to give you the meso compound. So we know the reaction is stereospecific because when we do it and you get anti-addition to the trans, you only get the meso compound. Let me just circle that. That's what you actually get. And when you do anti-addition to the cis, you only get the enantiomers. So the reaction is completely stereospecific, and there will be cases where you're going to have to analyze a product to determine what alkene you started with, and you need to remember that you need to work with the stereochemistry to do that. So that was my selling point on that one. Then before I go on and I start to work problems that I uploaded, I want to ask you, are there any specific other problems that you want to see? And you can unmute yourself and ask. I'm going to take that as a no. Oh, no? Okay. So the first things I've done here are from the textbook, and they are really just drill problems about remembering which reagents do which things. So at this point, they're going to, of the book and moving forward, they're going to throw at you a lot of reactions. And the challenge is to put the reactions together in short synthetic sequences. So it's kind of like solving a crossword puzzle. You're better off if you have a large vocabulary. And your vocabulary here is simply knowing what these reactions do and remembering that the stereochemical outcomes are important. So if I look at this first, starting with this alkene, and I start with the one going up the most, what I see has happened is that I have gone from having a pi bond to having a completely saturated hydrocarbon. And to do that, I can simply add hydrogen on platinum or palladium. And those reactions happen, it's syn addition, but it isn't going to matter here. Still give me the same product. When I look at what I have here, I'm starting with an alkene and I'm ending up with a halohydrin. And what gonna and the bromine is on the opposite side to the alcohol. And I'll show you this in a minute. So what's going to happen here is instead of doing the bromination in a non-nucleophilic solvent, so instead of doing it in carbon tetrachloride, for example, I'm going to use a nucleophilic solvent. And in this case, that nucleophilic solvent is going to be water. Now, water is not as good a nucleophile as bromine, but it's the solvent. It's simply that it is highly more accessible, if that's English, but it is more accessible. So the reagent here is to add bromine and water. And of course, you're going to get the enantiomer. So the first thing that happens is I'm going to form, and I'll just do it going up this time, that bromonium ion. And the next thing that happens is the water comes in. I had a excuse me, I am getting ahead of myself. I had a methyl group going down. So there's my methyl group. So the water is going to come in. And then the bromine is going to release. And that water coming in is coming in SN2-like, so that now I'm doing the other enantiomer. So now the methyl group is going to come up and the bromine is going to be coming up. So I get the methyl group coming up. And in the next step, since I am only have water, that water is going to come in and act as a base and deprotonate this guy, so I get a little bit of acid at the end, so that we would have water coming in. Actually, yeah. And then I get the halohydrin. Now, these guys are also really important synthetic intermediates. And the reason is that what I have here, I draw my ring, and I'm going to draw they're on opposite sides. So let's just say, which do I have going down? I have the bromine coming up. Doesn't matter, they're on opposite sides. So that's the halohydrin that I've got. And what I can do in the next synthetic step is I can react this with a strong base, for example, sodium hydride. And the strong base is going to deprotonate the alcohol to give me I haven't quite left myself enough space, but we'll make it work. And so now I have a nucleophile and I have a leaving group within the same molecule. And what happens is this comes over here and kicks that out. It's an SN2 reaction. It's an intermolecular SN2 reaction. And what I form is an epoxide. And those epoxides as three-membered rings are really important synthetic intermediates. They're very reactive, and they're very reactive because of the three-membered ring being strained and susceptible to subsequent reactions. So that will become important. How you form it, you can do it now, but the use of them will come up in the chapter in Organic 2 on ethers. So what I see here in the next example is I've gone from a cyclic molecule to a linear molecule. And I'm going to emphasize here that one should always count carbons because it's really easy to lose and gain them. So 1, 2, 3, 4, 5, 6, and 7. So I'm breaking that bond. And I notice that in the product, I have an aldehyde. So that means I must be doing ozonolysis, but I have to be doing it under reductive conditions. And I know it's under reductive conditions because I have an aldehyde. So we're going to do O3 with dimethyl sulfide. And we're using that reductive to make sure that I get the aldehyde. Aldehydes are delicate molecules. They react easily. And so you have to be careful if you want to make them and that you don't destroy them by making them. I've actually done that a few times in the lab. In the next case, what I see is that I'm adding OH. I'm adding OH to the less sterically hindered carbon, and it's going to be syn addition so that I'm adding the hydrogen and the OH on the same side. So if I wanted to draw in the hydrogen here, the hydrogen would be coming up. So this is hydroboration. And I'm going to use BH3 in THF. That's step 1. And then the workup to get my product is by adding peroxide and base, H2O2 and NaOH. So that's really just reaction drill. I ended up only needing 1 page. Okay, so this is also reaction drill. In the first case, I'm ending up with a ketone and I've lost a carbon. So I started out with 6 carbons. I'm ending up with 5 carbons. So I had to break a carbon-carbon bond. And just as an aside, I don't know what the weather's like where you are, but we're starting a massive thunderstorm here. So if I lose power, that's what happened. So we're going to cleave this with ozonolysis. It doesn't really matter whether I do this under oxidative or reductive conditions because the other product I'm not giving you, I'm just giving you the ketone. So here we'll just say I did ozone with DMS, dimethyl sulfide. In the next case, I'm adding bromine. I'm adding it to the least substituted carbon. So I'm doing anti-Markovnikov addition. And to do that, it's HBr and peroxide. In the third case, I'm doing anti-Markovnikov addition to install an alcohol, and that you do with BH3, THF, and then sodium hydroxide and peroxide. This next one might be a little bit difficult to see on first glance. What I'm doing is I'm making a diol. So I've got two alcohols here, and there are two ways of doing that. Way one is I can take this and I can make it the epoxide. So metachloropurbenzoic acid. And the reason that it's metachloropurbenzoic acid is that it's a solid. So I could use another peroxide, but I have an easier time handling and weighing a solid than I would with a liquid peroxide. So this is just really convenient as a solid. And what I would get initially is the epoxide. And then I can work that epoxide up with acid. And when I do that, I'm going to break the epoxide. Not just drawn it backwards. And that's good. The couple of other ways I could do it, because I'm not worried about stereochemistry, because I have this end is not, neither end of this is what's called a prochiral center. So by prochiral, I mean that when I react it isn't going to give me a chiral center, and it isn't, because in both cases it's symmetrically substituted. So I don't have to worry whether I'm getting syn or anti-addition here. The other way of doing that would be by osmium tetroxide. So I could also use and then to make it catalytic, they use NMO. And the reason that people don't like that reaction is that osmium is very toxic. The third way I could do it is with KMNO4 in base, but making sure I keep it cold. And the reason that I don't like that method is that even though I keep it cold, KMNO4 is a rather harsh reagent and I still get some side products. So if I were voting for a best method, I would vote for using peroxide and then cleaving it. So that's that one. Then we have to go to the, let's see, where am I? That was, okay. Yeah, so I'm here, and this is I'm adding bromine to the least substituted side, the alcohol on the other side. So this is Br2 in water. And then in the next case, I'm simply forming the alcohol at the most substituted side. So that's just Markovnikov addition H3O plus. Usually sulfuric acid would work really well. You prefer an acid with a non-nucleophilic anion. And then down for this guy, I'm adding bromine to the more substituted side. So HBr will do that. And here, I'm going to go from having the bromide to doing the elimination to this alkene. And to do that, I want a base. So that will do the elimination for me. And then down here, I'm doing a hydrogenation. And here on the next one, I'm forming now a syn diol. So I'm stuck using either osmium or KMNO4. So either here, and then in the one below, I'm forming the trans diol. And so this is metachloropurbenzoic acid, and then acidic workup. So questions about any of those so far? No? No? So these are just predicting the products. This rhodium compound is a soluble hydrogenation catalyst. And the beauty is not so much in doing this type of reaction, but what happens here, what's happened here is that researchers have made this so that the phosphorus ligand that's hanging off becomes a chiral ligand. And then when it's a chiral, you get asymmetric preferences. So the way that you would simply do this is syn addition. And so you would get the two methyl groups either coming up or both going down. And it's the same thing because of symmetry. Then B, I'm simply adding acid, and we're going to assume it's an acid with a non-nucleophilic conjugate base. And so that's going to simply put an OH group on the more substituted carbon. 1, 2, 3, 4, 5. 1, 2. This now is hydroboration, so I'm going to make a primary alcohol here. In the next case, I'm going to get anti-addition to the alkene. So one OH will go one way and one will go the other way. So the trick to this question is to realize that H2S is an is going to work analogously to H2O. So it's an H2S in this case is nothing more than a nucleophilic solvent. And so the product I'm going to get I didn't really need to put the ME there, it's understood, but okay. So that is the product I'm going to get plus the enantiomer. So far here, it's very noisy, but no rain. Suggest an efficient synthesis for the following transformation. So when I'm looking at this, the first thing I think I'm going to need is to get to the alkene, and then I can manipulate it from there. So in order to get the alkene, I need to do an elimination reaction. My alkyl halide here is primary, so I'll take it and react it with a base. And that will get me the alkene. In the next step, I'm going to, because eventually what I want is, what I'm thinking about is that I need the double bond here to do the addition. So I've got to move the double bond. And now in order to do that, I'm going to react this with something that's going to put a halide there that I can then do another elimination step to get me the more stable alkene. So in the next thing that I'm going to do here is react this with HBr, and that's going to get me the bromine here. And from there, I can do another elimination. In this case, I want to make sure I use a skinny base so I get the thermodynamic alkene. So I'll take that with sodium ethoxide. And I get the internal alkene now. And now what I want to do to get to my final product is I have to remember that there's a hydrogen coming up here. So I'm installing an alcohol, and the alcohol is going to the least sterically hindered carbon, and it's on the same side as the hydrogen. So that's syn addition. Step 1, step 2, NaOH, and peroxide. So the apex pose that is going to be part of almost every chapter from here on out is going to be putting together short synthetic sequences. And of course, I do get the enantiomer. Then, well, I shouldn't say it's the only apex pose because there's a couple of other kinds of apex poses. So one type of apex pose is retrosynthetic analysis and getting the forward reagents. The second part of that is looking at the reactions that you know and figuring out a reaction mechanism. So I'm going to have to take these separately because I didn't leave mine, I should have spliced them and put them in two different places. So it looks like what I've started here is I have an epoxide, and let me count some carbons. If I count this, I've got 1, 2, 3. So 1, 2, 3. So when I look at that, it looks like what's happening is that I'm going to have acid. The acid is going to do a proton transfer. In this case, it's going to proton transfer to the lone pair on the epoxide. That's going to make it a better leaving group. And in the second step, the lone pair from the alcohol is going to act as my nucleophile. So let me draw all that out. So we have H3O plus, and you can use H3O plus whenever you see a strong acid. And notice that the acid here, sulfuric acid, is put in brackets, and that means it's acting as a catalyst. It's not there in stoichiometric quantity. So the first step here is a proton transfer. And that gets me and so now that the oxygen is protonated, it's making that internal OR leaving group a better leaving group. So now this guy is coming in as a nucleophile. It's going to attack that carbon, and that guy is going to leave. And note that this internal SN2 reaction is coming in underneath. So the bond here to that oxygen is going to be down, and the OH group is going to be up. Let's see, I gotta draw this. So it's going to be 2, 3. And then we've got to do another proton transfer. Since I'm in aqueous solution and I'm in aqueous acidic solution, water has to be my base. That doesn't look big enough to be the oxygen. So that is your product. Now I need to grab this guy and move him down. I'll just redraw it and I'll take it all the way. Nope. Let me do this. Okay, I'm going to try and draw him down here. See if I've got it. Yes. Okay. So this is a similar kind of deal. The first step is going to be proton transfer to protonate the epoxide. In the next step, I have to realize that the alkene can act as a Lewis base, so as an electron donor or a nucleophile. So the pi electrons are going to end up doing the nucleophilic attack in the next step. So first step, we have concentrated sulfuric acid. So I've got H3O plus. Comes over and gets protonated. And then in the next step, oops, I forgot to draw the proton here. There we are. So in the next step, the pi electrons are going to do nucleophilic attack, and that's going to open. But notice that because of the way I've done this nucleophilic attack, I'm actually forming a ring. I don't want to draw it the other way. Make it easier for myself. So that came in there. And so I've got this over here. And it's a carbocation because it lost its pair of electrons. And now off of this guy, I've got those two. And off of this one, I've got OH. So a couple of questions. Why do I form the bond to this carbon and not the other one? And the reason for that is I get a tertiary carbocation, which is more stable. So that's why you form that 5-membered ring. I have a carbocation now, and I have acid, and I have water. So water has to be my base that's going to do the deprotonation. So what I haven't drawn here is there is a hydrogen here, and the water is going to come in. Do that, and those are going to move down there. And that is my product. Whenever I am doing cyclizations or breaking rings up, it really helps to count carbons. So if we started here, I have 1 in my ring, 2, 3, 4, 5, 6, and then I'm forming the bond to carbon number 2, so I get a 5-membered ring. So that is helpful. Then this last one, hard to see. So I'm going to treat this alkyl halide with a strong base to give an alkene, and then convert it by ozonolysis to this next product is why I'm going to do this. So the thing to recognize is that my 5-membered ring here is here. And the double bond I'm going to form is going to be there. So to form the double bond, I need to get an elimination reaction. So step 1 is to take this with sodium ethoxide, good strong base, and that's going to get me that. In the next step, I'm going to do an ozonolysis. Notice that I have aldehydes here, so I need to do my ozonolysis under reductive conditions. And that's going to get me a 5-membered ring, and my 2 aldehydes, which are coming here and here, are on the same side. So I could draw them both up or both down. It doesn't matter. They're just on the same side. So that's that mechanism question. And I have one more mechanism question. Plausible mechanism for this reaction. So let's count some carbons. I've got, so this methyl right here is the methyl that's coming off right there. And then I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. And that's likely coming out that one and then the other double bond. Okay, so how am I going to do this? What looks like it's happening to me is that I'm going to try and brominate it, but now my alcohol is at the other end of the molecule. So it's kind of like having water around, but it is even more effective than having water around because it's an internal, intramolecular reaction. I get intra and inter confused all the time, so sorry about the hesitation. So what we're going to do is we're going to react this with bromine. um, to get a bromonium ion there. And now I have an intramolecular reaction. And intramolecular reactions are, in fact, quite fast. So they're set up to go. And generally, if the choice is between an intramolecular reaction and an intermolecular reaction, the intra, which is the same molecule, will happen faster. So what that gives me six. six-membered, and we're going to have, let's see, methyl group here, oxygen up here, hydrogen coming off of there. Next to that, I've got this and the bromine. So the bromine is coming up that way. So I've got one carbon and then the bromine, and then the other methyl group, and then that tacked there. And this is, let me do some color. This is this one coming off of that. So that's what I get first. And of course, this is going to have a positive charge and a lone pair of electrons. And in the next step, it is going to have to get deprotonated. And I haven't specified a solvent for this reaction. So the only thing I have available for proton transfer is the Br minus that I got from that first step. And he comes down there. And then what I get is that guy. So that was a bit tricky. And then I have another tricky one, also from the integrated problems in the book. So what we know here is I've got I2, and we know that iodine can do the same kinds of reactions as bromine. It's kind of slow, and then iodine is a really good leaving group. So it looks to me what happens is I've done that iodine addition, and then if I had to look at what my nucleophile is, it looks as though the nucleophile is the lone pair of electrons on the carbonyl. So in step one, we get an I. That's that. This is this guy. Comes down, up, carbonyl, OH. And so this guy is going to attack that way, and then those leave. So that gets me iodine coming up. This guy attacked from the back side, so it's going down. And I need a how many membered ring? 1, 2, 1, 2, 3, 4, 5. And that's going to be an oxygen. And this now is still double bonded. And I have an OH out here. And then this guy already was coming down, and he's coming up there. So now I've got to do another proton transfer. And that means that my iodine is going to be my base. It's going to pull off this hydrogen, and then the pair of electrons are going to, these electrons are going to go in to form a double bond here, and the electrons in the double bond are going to go up to the oxygen. So how does that work? So I have I minus out here. It's going to come and pull the hydrogen off. Those electrons are going to go in there to form a double bond, and those electrons come up there so that, oh, I should have drawn also at this point, this guy's got a positive charge and neutralize that positive charge because there's 3 bonds to oxygen there. So when all of that happens, I have, that's an iodine, iodine coming up. This is going down. I keep wanting to make it go down as I'm It's going down, but it has to point up here to get me the 5-membered ring. Oxygen. And this comes out here as a carbonyl and down there. Whoops, not a carbon there. It's a carbon, not an oxygen. So I have an ester in a ring, which is a lactone. Cyclic ester in a ring. So that's how that one works. Did I have any others? Oh, I did put one more in here. Okay. So in order to get the trans bromide, I had to have been adding something to a double bond. So how did that work? And I must be somehow, yeah, I added it to a double bond. So what I'm going to say happened first is that the electrons in the pi bond are going to attack the HBr. So these guys come out here and that leaves. And what that's going to get me, since HBr is going to add Markovnikov, and I've added a hydrogen here, which I'll just do that to make it explicit. So you've added a hydrogen here. So now there are 2 hydrogens on this guy. So I have a carbocation and it's next to the bromine. And I'm just going to draw one enantiomer here. So what happens now is a lone pair of electrons comes in and attacks that carbocation, and I'm forming now a bromonium ion. So now I have a bromonium ion. I have a Br minus that's still floating around from this first reaction. It's going to come in, do a SN2-like reaction. So what I would end up with is this up, that guy down, plus the enantiomer. So that's like seeing a wrinkle in the reaction mechanisms that you've already done. The hint that you have to be adding bromine across a system or bromonium ion is that you don't get any syn addition. So what you're looking for is a way of getting a bromonium ion somehow. And the way that you did that was by taking the pi electrons acting as a Lewis base and doing proton transfer to HBr. And of course, you get plus Br minus here. And in the next step, that Br minus acts as a nucleophile on the bromonium ion, and that gives you anti-addition. And I'm pretty sure that's the last one I had. So questions about this chapter, anything about this chapter, and I will try and find my video recording of part 1 of the chapter and upload that also. It takes a while for that stuff to render. So other questions?